We are UB Team 42, and this is our presentation video for the PEP 2024 competition. Without further ado, let's jump right into the details about our electrical system.
Hi, I'm Evan. I'm here to talk to you today about the electrical diagram of our electric boat. So just a quick overview to get us started. We have batteries up here, which lead to an inverter, and then to a variable frequency drive, and finally culminates in a 5 horsepower electric motor. So as we go through, we're going to start at the batteries and talk a little bit about those. So I actually have one here. It's a lithium iron phosphate battery. So we chose this type of battery for a couple of reasons, mainly because of its stability and, relatively speaking, lighter weight. The initial idea was to go with lead acid battery, which are found in cars, but those are extremely heavy and we didn't want to weigh down our boat like that. A secondary idea was to go with lithium ion, but those aren't as stable and we wanted something really stable for safety. So we ended up with this. However, we need 24 volts to drive our inverter, so we actually take 2 of these, put them in series, and that gets us a total of 24 volts. However, that only has a 100 amp continuous rating and it just wouldn't have enough charge to get us through the 5 miles. So we actually take another bank and put it in parallel. So we still have 24 volts of total charge, but it's distributed amongst 4 total batteries. That gives us a 200 amp continuous rating and an expected life of about 1 hour and 20 minutes at the full rated 5 horsepower, which should be pretty good. So from the batteries, we actually have a fuse. This is a 200 amp fuse, and it's a slow break. We're gonna be nearing 200 amps for most of the course, but we think it's a good place to be. From the fuse, we then go to the inverter. So this takes in a 0 to 24 volt signal and pumps out a 0 to 220 volt AC single phase. From there, we actually have another set of fuses. This is a 25 amp fuse and goes on both the neutral and positive lines. This is an industrial safety rated fuse, and it should keep us in a pretty safe spot in case there's any shorts. From there, we then go to the variable frequency drive. As the inverter only spits out single phase, it doesn't really have any control over what speed we could be going. So we take the variable frequency drive and then we can actually modulate the speed at the electric motor is going. And that allows us to putter along going slowly or speed up when we need it. From there, we then go to the 5 horsepower 3-phase electric motor. This is what's finally powering our system, and it's beefy and it works quite well. It's very reliable and extremely smooth. So it's actually possible to overdrive this a little bit with all of our system. We have a little bit of leeway built in where we can actually overdrive the motor a little bit beyond 5 horsepower, but that's still in testing. On top of that, we want something for safety. Because these are breakers, they'll trip in case of a short or overcurrent to protect our wires, but we need something in case the driver falls off. So we actually have a man overboard switch as well. That's a safety lanyard. In case the driver falls off, it'll activate this relay, which disconnects the 200 amp line and puts us dead in the water. So this is our electrical diagram, and that's about all I have to share about it today.
Hey guys, so I'm Sean. I'm gonna explain the electric system in our board. Okay, so we have 4 batteries, so each 12 watts capacity, and we have a 2 bus bar and the power getting to the 2 bus bar, and we have 2 breakers. Okay, this is 200 amperes and this is another breaker, and this is 1 safety switch. So I'm gonna get to the power. This is another safety switch and you hear the sound, and now I'm going to turn it on the 200 amperes, and I'm going to turn on the inverter and the safety switch. It's ready to run, and this is the motor. So directly the power will be getting to the motor, and that's how the motor system going to work with the pulley and the rotor. And you can control the speed with this button.
Hi, I'm Matt, and I was in charge of the mechanical design for our propulsion system on our boat. So as you can see, much of the actual mechanical section of our propulsion design is hidden beneath this HDPE shield. So let me take that off with you. So as you can see underneath the hood, our design is actually quite simple, consisting of three main components. We have our 5 horsepower drive motor, we have our belt system, and then we have our boat drive. Due to the limited budget we had to work with, we had to be very cost conscious on where we source these components, as normally they would be very expensive. So this AC motor was sourced secondhand from an independent seller, and then this boat drive was sourced from an outboard motor shop that was initially going to discard it because it had no value to them. So we took both of these and were able to make a functioning system out of parts that otherwise would not have had much other use. So starting from the back, we have our existing boat drive. This was off a 7.5 horsepower gas-powered outboard engine that had been, again, flagged for not being valuable enough to sell, so it was going to be scrapped. So we are reusing the existing drive shaft within this boat drive. We are adapting it and coupling it to a shaft that we can work with, and we are driving that directly using this pulley system in order to get power down to our propeller. Now, due to our pulley system, we need a constant distance between these two pulleys, which means that we cannot actually pivot this boat drive right here. So that is why we have a separate rudder instead of being able to tilt this boat drive to be able to turn our boat. So moving on to our pulley system, one important thing to know about this drive is it is estimated that the power head ran at about 4,500 RPM underneath the gas motor. Now this electric motor has a rated speed of 1,750 RPM, which means we needed a ratio between our motor and our drive. That ratio was done using our pulley system that uses a A-series V-belt. We go from a larger pulley to a smaller pulley with a belt ratio of about 2.68 to kick the speed up to something closer to what the boat drive would expect. So another important thing about pulley systems is belt tension. So the way that we have our belt tension is we are actually using the weight of the motor, which is mounted on hinges, to give this belt a tension force to it. So you can see as I pull this belt together, the motor will actually raise up, as again, it is simply just mounted on hinges. So then to our motor, this is a 5 horsepower, 220 volt AC, 60 hertz motor, again rated at 1,750 RPM. We are driving it with a VFD, variable frequency drive, in order to determine the speed of it, or just the speed of it. And then that, again, is directly connected to our drive pulley, which goes to our motor. That's pretty much all the details about the mechanical part of our propulsion system. Thanks for listening.
Hey guys, my name is Joe. I'm in charge of the structural components on our boat for this competition. So our boat is a 16-foot wooden hull that was generously donated by the Buffalo Maritime Center. So let's take a look. So starting from the back, we have a fully wooden support that's connected to the transom, which the support holds our rudder, which is from an old sailboat actually. And this rudder can go fully up 90 degrees for ease of transportation. To keep it in 90 degrees, all you need to do is tie this rope to the inside of our support. Moving along, we have a HDPE shielding, which is all over our engine pulley system. This shield is mostly used for protecting our motor from any potential unwanted water coming in, as well as keeping hands away from the speeding pulley. So as we move along, we then get up to our electronics box, which is shielded by a polycarbonate shielding. Same as before, the shielding is to keep any water that may come into the boat away from our high voltage electric system. Now, the VFD and the inverter are mounted on the back of this box for having a secure spot for these important components, as well as having it in one spot for our captain. Moving along, we have the mid deck, which is where we would keep our 4 12-volt batteries. Each battery is supported by 3 wood planks, one on 3 of the 4 sides. Now, this is in order to keep the batteries in one spot during the competition, as well as to create a little bit of spacing so there's no overheating concerns. Also on the mid deck, we have our plank, which is responsible for clamping down our low voltage electronic components. So our final stop on the boat is the command center. On the command center, we have the controls, which has our captain's seat, as well as the kill switch. So if anything were to go astray during a competition, all our captain would have to do is pull the kill switch, and that would get rid of all of the electrical current going through our system. Now the final thing is the steering system. The way it works is we have this wooden plank that, when pulled right, will turn the rudder and ensure the boat will then turn left. In the same way, if you pull the plank to the left, then the boat will then turn right. Now the tightness of these strings will be ensured by these clamps, because we need the most tension to make sure that we have efficient control of where our boat will go. And that's our system. Thank you.
Hi, my name is Andrew. I've been in charge of implementing our technical innovation, one of the major technical innovations, the efficiency monitoring system of the boat. The efficiency monitoring system of the boat, the intention is that we'll be able to deliver an exact efficiency that our system is running at to the captain, who can adjust that on the fly, adjust the speed of the boat on the fly. So to do this, we start right here at the back of the boat. We have a pitot tube, takes water input from the source right at the bottom here, feeds through this black tube, all the way up here, where we have a pressure transducer. This pressure transducer is going to read the pressure of the water coming through the tube, and it's going to output a signal between 0.5 and 4.5 volts to our Arduino control board. Secondly, we have right here a single phase Hall effect current sensor, which is reading the single phase AC current flowing through the wire. And that's going to output, again, a 0 to 5 volt signal to the Arduino board, which will be able to determine exactly the amount of current going through the AC system. And since we know the voltage through there is constant, we'll be able to determine the exact amount of power being used. Coming up here to the control center, all the information is being output to the captain through this 4-digit 7-segment display. The current sensor has a 3.5 millimeter jack that's going to go right in here, and the system here, the 5-volt power is going to come in from the board through this red wire here, goes through a 10 ohm resistor. This resistor here, returning it back to the ground, is also 10 ohms. Passes through a capacitor, which just keeps the current within the DC system powering the current sensor. It keeps that constant, so that way we're not influencing the output of the current in any way through the DC system. And all of this code is going to be stored on the Arduino board here, locally on the board, so no other computers will be required for this system. The signals from the 2 transducers come in through the analog ports on this side of the board, and the output to the display comes from the digital ports on the other side of the board. And that's about all there is to it.
All right, so I'm just going to do a quick overview of the code behind the electrical energy monitoring system. So first, this entire section right here just initializes all the different variables that are used within the system, and we're also including the emonlib.h library, which is right here. Now this is created by Open Energy Monitor and is publicly available online. This is a great tool which is used in the current monitoring part of the system. Coming down here, the void setup section, which is all this right here, runs once. As soon as the board receives electricity, it is going to run this section of code only one time. Now what this does, it initializes all of our pins, serial communication, and this part is calibrating the current monitoring system with a 17.5 calibration factor. Down here in the void loop section, this is going to run over and over again until the board loses power. The first section here, energy monitoring system, is going to calculate the current, then the apparent power, and then it prints it all to the serial monitor. Speed monitoring system right down here, this part calculates the pressure, and then the speed. These are both based off of Bernoulli's equation. The pressure is based off of the 0.5 volt to 4.5 volt input, and the 1023 different values that it will output through the analog pin. Again, we're just printing that to the serial monitor. Down here in the display section, the first part, it's going to check display mode. So there is a section of this code for each display mode. The first one here corresponds to the power, and these 5 different sections right here are just splitting it up into different sizes of numbers. So for any power that is greater than or equal to 1000, so aka 4 digits, this will set the 4 digits right here. If it is only a 3-digit number, it's going to set the first digit to 0, and then the last 3 digits are going to be the power value, and that continues all the way down here to single digit. And then if the power is greater than 10,000, which it should not be, or less than 0, which again it should not be, it will display 0. And then down here, this is just writing all the digits to the display. So first we're going to select the first digit. So we're writing to the first digit right here, pin 1 high. And then if the number is 0, we are going to write 0. If 1, we are going to write 1, etc.
So what makes our boat unique? So one of the key differences compared to commercially available electric boats is that our boat is made of a wooden hull rather than a fiberglass hull. Now, fiberglass hulls have lower densities, which will in turn allow the boat to have more efficiency as well as reach higher speeds.
Additionally, the components that we've used for our control system and propulsion system consist of mostly off-the-shelf parts or ones that we were able to source from retired machinery. Now, in a commercial application, most of these parts would be integrated to save on cost and also space that's occupied. Moving back to our propulsion system as well, we're utilizing a belt and pulley system to drive our motor. In commercial aspects, they would most likely use a direct drive motor instead of a belt and pulley system.
Now here's a quick tour of the Maritime Center. This is the cold storage area, which is where we worked on our boat. Next is the Antique Boat Workshop, where all the antique boat projects are worked on. This is the wood shop, which is where all the woodworking machines are and where a lot of our components were fabricated. And finally, we have the machine shop, where metal fabrication takes place. So that is our presentation video. From everyone here at Team 42, we thank you for your time and are looking forward to the competition.